baby shark, do 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 do, baby shark, do 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 do, baby shark. Mommy shark, do 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 do, mommy shark, do 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 do, mommy shark, do 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 do, mommy shark. Daddy shark, do 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 do, daddy shark, do 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 do, daddy shark, do 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 do, daddy shark. Grandpa shark, do 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 do, grandpa shark. Hello, welcome back to Simon the Scientist. This week we are going to be doing stellar evolution, which is basically what happens in different stars of life. So in the first 30 seconds of the start of the thing, you saw a picture of a stellar evolution hypothesis. I'm pretty sure that's how I pronounce it. And yeah.
All right, we have some questions here for you.
So the reason why I chose astronomy today is because my mom has been having astronomy courses, and from what I heard, I think it's very interesting, so I wanted to do Simon the Scientist about it.
Simon, what do you already know about astronomy?
I know that the universe is endless. There are multiple galaxies in the multiverse, in the universe, and stellar evolution.
What do you like about astronomy? What do you find interesting?
I just like finding out new things, that's all.
Cool. Guess what? Auntie Camille says hi.
Hola.
We have to find out if all the kidlets are watching too.
Okay.
All right. We have a special shout out today.
A special shout out to Pence.
Yeah? Who's that?
The teachers in astronomy that you've been teaching.
Yeah, they're pretty cool. And you know what they were asking? They were asking for a special shout out because they love astronomy too. All right, so you have a joke for us to share, I think.
Why is moon rock better than Earth rock? Why does moon rock taste better than Earth rock?
Why does moon rock taste better than Earth rock?
Because it's a little meteor.
Very nice. Do you want to tell one more or wait a few minutes?
Wait a few minutes.
All right, here we go.
So to get into the actual Simon the Scientist, other than jokes and shoutouts.
All right, let's get into actual Simon the Scientist. So we have a really cool diagram here. Can you explain it to us?
So this is a photo of stellar evolution. So a star's life starts as a nebula.
What's a nebula?
So it's basically a cloud of gas that happens when a star explodes. And eventually, over a couple million years, it'll turn into a main sequence. So a main sequence star would be like our sun.
Okay.
And then after the main sequence star has used most of its hydrogen and helium, it will expand and turn into a red giant, and then explode into a planetary nebula, and then group together to create a white dwarf out of its remaining atoms.
Okay. What's planetary nebula?
I have no idea.
Oh, would you like to know?
Sure.
All right. The planetary nebula is all of that dust and gas again that explodes and comes out when the star death happens.
Well, why can't it just be a normal nebula?
Well, first of all, it starts as that planetary nebula because you have all of this immediate explosion, and then eventually it regroups and reforms and becomes
a white dwarf.
Oh, the white dwarf is what remains, but the nebula, the dust and gas, eventually reforms to become a new star again.
Around the white dwarf or completely new?
Completely new.
Oh.
Completely new.
So a white dwarf is basically just an empty core.
Pretty much, yeah. You got it. All right, and what happens with the high mass stars?
So it's the same thing. So it goes from a nebula into a main sequence. But instead of just a normal red giant, it turns into a red supergiant because it has very high mass. And then it turns into a supernova, not a nebula. A supernova is a very large explosion, kind of similar to a nebula, except it's on a much larger scale. And then it either turns into a neutron star, and if it's very, very high mass, it turns into a black hole.
Oh.
I wonder if Sagittarius A once was a really big star with high mass.
What is Sagittarius A?
The black hole in the center of our galaxy.
Yeah. So it would have been at some point, but we could do some more research on that.
It's not like a gravitational space bucket appeared out of nowhere.
Space bucket?
Yeah.
Those space buckets, they always get in the way. All right. So we are going to do an activity to see if there's some kind of connection between what?
So, what we're going to do is, we're going to make a scale on stars. We have paper stars over here.
Okay, here, we'll move this image out of the way a little bit.
We just made some stars. So there's that one, this one, this one, this one, and eventually this one.
Okay, and we are going to see if their size and mass is connected to what?
How long they live.
Right on.
From what I've heard, the smaller the star, the longer it lives. But I don't really know that for sure.
What happens in animals? Is there a connection between a large animal or a small animal and how long they live?
I don't know.
Well, think about little bugs. Some bugs have a lifespan of like 4 days or even hours. And then you think about something like elephants. Elephants live a really, really long time.
There's a squid I learned about, and in its whole lifetime, it gets to be up to like 10 meters, but it doesn't even live a year. The most recorded longest living Magnapina squid was 315 days.
Wow. So it's really big, but a really short lifespan.
So each day it probably grows about like a couple centimeters.
Interesting. That's really cool. So I wonder if in animals there's a connection, but today we're going to figure out if there's a connection in stars.
Yeah.
All right, so here's your scale. What does this mean?
So 1 millimeter is 1 million years. 1 centimeter is 10 million years. 10 centimeters is 100 million years, and 100 centimeters is 1 billion years, aka 1 meter.
That's right. Okay, so you've got your trusty tape measure. You've got some
Yes, sir,
paper.
I got this from Canadian Tire a couple days ago.
Pretty exciting. You've got paper rolls. Let's see those. Or you can just grab one of them.
We are just going to be using these for scale.
Yep, and if you don't have a paper roll like this, you can just cut a strip of paper on a regular piece and tape them together. And Simon, you have a decision to make. Do you want to start with the smallest star or do you want to start with the biggest star?
Oh, but what if I just
Okay, you decide. Which one? Tell me. You can decide. Which star are you starting with?
Ouch. Okay.
Okay, so that one's right in the middle. So this star's name is Sirius. Can you pass me the red marker?
It's not Sirius. I'm pretty sure it's pronounced Sirius.
Okay.
Sirius. I have no idea.
All right, so we'll start right in the middle here, and I'm going to put an S on it. just so we know.
It's stands for Simon series.
Oh, the star is now called Simon. Okay, so here's some information. Compared to our sun, how big is it?
Sirius is times 2 to the mass of our sun.
Okay.
Hydrogen, 1 billion years.
Okay, so what we're measuring is from the time that the hydrogen fusion started,
1 billion years.
and then the star death is after an additional,
10 million years.
so let's do the scale. So first we have to measure out 1 billion years.
1 billion.
So on your scale, how long is that?
100 centimeters.
All right, let's do it. So let's get this, get your tape measure.
I am going to the underworld to get a tape measure, and then I'm going back up to the normal world.
All right. Welcome back from the underworld. So let's put a piece of tape here where we're going to start. You can tape this to the table. Now you need to measure how much. 1 billion years, you need to measure how much?
1 meter.
All right, let's do it. I'll step back a bit. We've got all of our papers here that I'll get out of the way.
So, 6 centimeters.
Okay, so this is centimeters on the bottom here, and we are at 10. We need to go all the way to 100. So you keep your tape measure set there, and we have to measure out 100 centimeters. So here, I'm gonna help you with this. I'm gonna hold your tape measure here. And no, because we need to keep going here. And you see how far 100 centimeters goes. So take your tape measure with you too. Yes, there we go.
$1 billion years.
Okay, so put a red mark at the 100 centimeter or the 1 meter mark.
We're supposed to lock it.
Mm-hmm. Now we need to add on the time that it takes for the star to die, because it's not just instant, not completely instant. So now we're adding on another,
10 million.
which is how many centimeters?
1.
Okay, so you need to add on 1 more centimeter. And make a mark there. Yeah. Good stuff. And we can cut the paper
Big boy scissors.
after the second line there.
Big boy scissors. Unlock.
Yeah, you can unlock.
You can unhold it. Why does it say you can unhold it?
We all have funny language sometimes. So this line represents the lifespan of
A couch.
Sirius. Pretty cool. All right, so this was the middle star that we had. So let's put it in the middle of the table. And
Big.
we'll put this in the middle of the table, and we'll tidy it up a bit here. Well, hang on, guys. Sorry, I don't mean to be moving the phone around like that. All right, what star would you like to measure next?
Tiny boy.
The tiniest one. The tiniest one is named Alpha Centauri B. So you can label it ACB.
Akaba.
Yeah, Akaba.
Only if the B and the C were switched.
Yeah, that would have been cool.
A, B, C, D.
Okay, so we're going to do the same thing that we just did. We're going to measure the scale. So let's bring it over here. You can put a piece of tape on the end to keep it still. And And what do we know about the size of Alpha Centauri b?
That is bigger than our sun.
It's bigger? It's point,
8 times.
so if it's 0.8,
Oh, it's smaller.
it's smaller than our sun.
It's 8 times smaller.
So let's see what happens with its lifespan. You need to measure out how much time from the start of hydrogen fusion. What are you measuring out?
Centimeters.
How many?
7.
No, look at. We're measuring 20 billion years.
Which would be 20 meters.
20 meters. Do you think we even have enough? Let's find out.
I need you to hold this.
20 meters.
I need you to hold this.
Okay, I'll hold it on this side here. Let's see how far we can get.
Should I let it fall?
No, go to 1 meter. Go to 1 meter.
1 meter?
Yeah.
Times this by 20.
Times 20. Yeah. So let's see how long the whole roll is. Yeah, you can let it fall, but let's keep measuring it all the way even towards the couch. Let's see what happens.
Be free, my child.
There it goes. Keep measuring.
That's the end.
That's the end of it. So how many meters does this tape measure have?
12 feet. It only goes to 4 meters.
4 meters, and we need to do 20 meters. So look at
15 less.
outside the window there. Do you think we would be all the way at that snowbank outside the window?
Probably half.
All right, let's have a look. So we don't have enough paper to do this one, but we know that we would be probably all the way at the snowbank outside the window.
We'd probably be jumping in the creek measuring.
Maybe. All right, what star should we do next?
We should take the biggest.
So we know definitely so far that the middle star lives a longer or shorter lifespan than the smaller star. Much shorter lifespan. You want to measure the biggest star?
Oh, my hypothesis.
So far, but we've only measured 2 stars, so maybe that could be a coincidence. We don't know for sure. All right, so let's measure the biggest star. Okay, now this biggest star is named.
A crux.
Okay, so you can label the star.
Wait, so I do AC?
Yep.
AC.
Okay. What do we know about this star?
15 times the mass of our sun.
Okay, and since the ignition of hydrogen, it will live.
10 million years, which is 1 centimeter.
All right, so let's start measuring. You're going to need a new roll here, a new tape roll.
Of course.
I'll get you a piece of tape ready here. Right there. Okay, so you can measure. Okay, since the ignition of hydrogen, it will live 10 million years, which is?
1 centimeter.
Whoa. Okay, measure and mark it down.
Yes.
That's it.
Yep.
Okay.
Like about here.
But then we can add on the star death, which takes another 1,000,000 years. I think the marker is bigger.
Let's just make.
The path of the marker is bigger than 1 millimeter.
Let's do that.
All right, and cut it off. Look at that.
Where will you go? You're gonna die so young. But boy.
All right, let's put the biggest one at the end of the table there so then we can see the size of
Like
it.
this star has a little chimney.
Yeah, it kind of does.
Chimney.
Okay, so put it so we
Where
can
the
see
little-
it
it's
towards
where-
the wall.
It's where the little wolf burns his butt.
Now, do you want to do the second biggest one or the second smallest star? Which one? We have two left.
Second smile.
Second smallest. So this star, well, let me grab my trusty information here. This star is
1 billion years.
Alpha Centauri A.
Alpha Centauri.
So you can call it,
ACA.
sure, sounds good. ACA is good. Okay, and let's start our measurement.
A plus.
Start our measurement. How big is Alpha Centauri A?
1 meter.
1 meter.
Yeah. There's also the sun, which means it's the same size.
Yeah, it's about the same size as our sun.
I wonder if we could live with this star at the center of our solar system.
Oh yeah, like if we could just trade them in and they would be equal.
Yeah.
Yeah, I wonder. All right, so we have,
I know it would be like having 8 crocks as of the sun.
oh, cool.
That'd be crazy.
Okay, so time from the ignition of hydrogen is how much? How much
1
time?
billion years.
So how much do we need to measure?
So 2 meters.
1 billion years is
100 centimeters.
1 meter. That's
I know,
right.
but this.
Oh, but wait, we'll get to that. We're just doing this piece first.
I know, but I'm just saying.
Oh yeah, you're looking ahead. Okay, oh, let me hold it here for you. Okay, so you measure out that 1 meter.
We'll hold it.
Yeah, I'll hold it. Whoop. There you go.
1 foot, 2 foot.
We're not looking at feet, we're looking at the centimeters.
Yeah, I'm just noting when it's.
Oh, you're transitioning back and forth between your measurements. Okay, so here you go, Simon. You can mark that 1 meter, which represents 1 billion years.
Got a locket?
Yeah.
I don't have a locket. I'm locking.
Yeah. Good. So Alpha Centauri A will live about 1 billion years. And then the process of its death will take an additional how much?
1. AKA 1 billion.
100 million years. But look at your scale. What is represented by 100 million years?
1 billion years. I mean, 10 centimeters.
Good. So add on another 10 centimeters to this star's life.
7.
Okay. Lock it up. Mark it.
Lock seems to be really useful.
Yeah, it is really useful. Simon's getting a lot of experience with measuring today. Okay, so you can
I shall unleash.
cut that one.
I shall unleash the magical measuring burp.
Simon.
I can burp at my own will. I've gained this legendary
He's crazy,
power.
folks. Let's not forget, he's 8.
I am not 8, I am 15
Okay, so
billion.
look at this so far. We have
3 stars done. I mean 4.
We have 4 stars done, and I'm just going to clear our table a little bit to see if we notice a pattern yet.
I can't believe 1 star used 1 whole roll.
1 star, we didn't even have enough for that. Look at that star needs to go all the way out of our house and down by the creek. That's
Into the creek.
probably into the creek in terms of its lifespan.
Across
Okay,
the earth and into my nose.
so look at this, Simon. We have 1 star left to measure out its lifespan.
Yes.
Now look at this. What pattern have you noticed so far? Look at that giant star. Only lived that long.
Yeah. Well, smaller stars live long.
Look at, you are starting to realize that smaller stars live, whoa, much longer.
I already knew that, but you doubted it.
You already knew that. Well, you said you weren't totally sure, but you thought so. That was your prediction. So sometimes our predictions are correct, and sometimes our predictions need to be revised. Yeah, there we go. All right, we've got one last one. Now, talking about predictions, how long do you think this last star will actually end up?
Probably like 3 times this one.
Okay, so maybe like halfway down the table? All right, so this star's name is?
Vega.
Yeah, Vega.
Vega.
And
Las Vega.
yeah, it is how big? Again?
Okay, 5 times the mass of our sun.
All right, Vega is 5 times the mass of our sun. All right, let's do our last measurement here.
If I add one more line, it'll look like a bird.
Yeah. Look, you have a roll of paper right beside you there.
This is the last remaining one.
Yeah, that's all right. We still have more, but it fell off the table and rolled away. Okay, so let's cut it straight to start with. And you can put a piece of tape down. And let's see the lifespan of Vega. And if it follows our pattern so far.
What do you mean by pattern?
Well, our pattern so far is that the largest stars have a shorter lifespan.
So,
Let's see if Vega follows the pattern. 100
100 million
million years is how long in our
is
scale?
10 centimeters.
Okay, I'll hold this.
So,
And then its death process takes,
1 million.
no, not 1 million years. Look
10
at,
million.
yeah, just 10 million years.
Which is 1 centimeter, so technically 11 centimeters.
All right, so you need to add on 1 more centimeter to this measurement.
Okay.
I'll hold that for you. Yeah, look at
Oh,
that.
now I know how big a centimeter is. Haha.
And you can cut that tape there.
Wait, cut that tape?
Yeah, or I sometimes call the paper roll the paper tape, I guess. All right.
And he waddled away, waddle, until the very next day. Ah,
Okay. So what do you notice? Come stand over here and let's have a look. What do you notice about the size of a star and its lifespan?
The size of the star, smaller the star, equals the longer it lives.
So was your prediction correct or incorrect?
Correct.
Do you think it's true for every single star or just most stars?
Most stars.
Yeah, sometimes things aren't true for every single star, but for most stars, it seems like the larger the star, the shorter the lifespan. The bigger the star.
Actually, the bigger the star means the longer it lives. So black holes live forever.
Oh, well, I guess so. If we're counting that part of it, you bet you would be correct there. All right, so Simon, you have a pretty cool conclusion there.
The smallest star thingies live forever.
Mm-hmm.
So which one wins?
Well, we would have to then investigate, is a white dwarf, what's the lifespan of a white dwarf, and a black hole? That could be our next session.
Yes, sir.
All right, do you want to tell another joke?
Because I remember doing an astronomy in the summer.
That's right. Do you want one more joke before we wrap up for today?
What do astronomers do when they have a party?
What do astronomers do when they have a party?
They plan it.
Very nice. And you can give the challenge for this week.
So the challenge for this week, well, it's not really a challenge, but the challenge for this week is to investigate some stars and find out your favorite facts about that star.
Yeah, and they can just post it right on the Facebook page.
Yes, sir. Adios, amigos. I'll be seeing you somewhere